Welcome to The Explainer. Today, we are skipping right past all those breathless viral news headlines to unpack the actual, rigorous science behind the potential discovery of alien life on exoplanet K2-18b. You've probably seen the rumors claiming we've found the ultimate evidence of life 124 light-years away. But what is the real scientific reality behind these massive claims?
So, let's dive into this huge question that literally everyone is talking about right now. We're going to explore whether these recent chemical discoveries made on a planet far, far beyond our solar system are just media hype, or if we are truly standing on the precipice of the ultimate breakthrough in human history.
To get to the truth, we're treating this like a cosmic detective story. Here's exactly how we'll break down the investigation. We'll start with the K2-18b mystery, move to profiling a Hycean world, then the ultimate magnifying glass, the DMS biomarker clue, the 5 Sigma standard, and finally, the final verdict.
All right, Part 1, the K2-18b mystery. Our story starts with a primary suspect, a mysterious world scientists have been tracking for years. And honestly, just getting to this point has been a roller coaster of engineering triumphs and near disasters. Back in 2009, NASA launched the Kepler Space Telescope to stare unblinking into the dark, searching for the tiny dimming of distant stars that tells us a planet is passing by. In 2013, the mission almost completely failed when its stabilizing reaction wheels broke. But brilliantly, engineers used the actual pressure of solar radiation to stabilize it, launching the refined K2 mission in 2014. And it was under that very mission, in 2015, that a strange new world was spotted orbiting a red dwarf star.
Now the math here is absolutely fascinating. K2-18b sits 124 light-years away and is classified as a mini-Neptune. With a radius 2.6 times larger than Earth, it technically should have a mass around 17 times heavier if it were purely solid rock. But its mass is only 8.6 times heavier. So this told scientists it's too light to be purely rock, but too heavy to be purely gas. The leading theory? It's completely covered in a massive planet-wide ocean. But there was a catch. Based on its distance from its star, its average temperature was calculated at -8°C. So shouldn't that massive ocean just be a giant block of solid ice?
Which brings us to Part 2, profiling a Hycean world. With our suspect identified, a brilliant Cambridge University scientist named Nikku Madhusudhan stepped in. His team realized we might be looking at this all wrong and created a specific profile for this exact type of planet. You see, instead of looking only for Earth-like rocky planets with oxygen, they proposed that these hydrogen-ocean combinations, which he named Hycean Worlds, are actually incredibly common in the universe, and they could be perfect incubators for life.
So, the crucial point here is that the thick hydrogen layer acts like a massive greenhouse blanket. It traps the heat and keeps that global ocean comfortably above 0°C. This model predicted some very specific chemical signatures. For one, ammonia levels must be extremely low because ammonia easily absorbs into liquid water. It also suggested that the extreme pressure at the bottom of these incredibly deep oceans could create exotic, clay-like ice known as I6 and I7. This ice could actually form a barrier over underwater volcanoes, creating the exact chemical conditions, much like Earth's own deep-sea hydrothermal vents, needed to spark the first pulses of life.
Okay, Part 3. The ultimate magnifying glass.
Now, a theory is just a theory without hard evidence, right? To prove this Hycean profile fit K2-18b, investigators needed to analyze the planet's atmosphere using a technique called transmission spectroscopy. The legendary Hubble Space Telescope tried first in 2018, and it did find water vapor. But if Hubble reading partial atmospheric data was like squinting at a fuzzy black and white TV, the new $10 billion James Webb Space Telescope is like suddenly plugging in a high-definition color screen. Hubble could only read a fraction of the story, leading to confusion between water vapor and methane. We needed something profoundly more advanced.
The difference in hardware completely changed the game. While Hubble could only look at a narrow infrared range of 1100 to 1700 nanometers, James Webb sees a massive spectrum, from 600 all the way to 28,000 nanometers. Plus, James Webb operates in extreme sub-zero temperatures, which eliminates its own electromagnetic noise. That makes it literally 100 to 1,000 times more sensitive. It can read the exact chemical fingerprints of a planet's atmosphere without any of that past confusion.
Moving right along to Part 4, the DMS biomarker clue. Armed with this incredible new telescope, Nikku's team stared intensely at K2-18b for a whole year, and when the data came back, it perfectly matched the Hycean world profile. They definitively found methane and carbon dioxide. They confirmed the expected low levels of ammonia, proving the massive liquid ocean theory.
But tucked away in that high-definition data, they also found something absolutely astonishing: a slight hint of a molecule called DMS.
What is DMS? Dimethyl sulfide. It's the literal smell of the sea. You know that sweet, slightly sulfuric cabbage scent you get at the beach? Crucially, on Earth, we currently know of absolutely no natural process that creates DMS in large amounts other than living, biological marine organisms like phytoplankton.
Finding something like methane is a great hint, sure, but it's like a whisper in the ear. It can be produced by basic geology. Discovering DMS on K2-18b, however, in quantities thousands of times greater than what we find on Earth, that is a massive, unmistakable shout that life could be present. As a biomarker, nothing else even comes close.
Part 5. The 5 Sigma Standard.
This sounds like case closed, doesn't it? Well, before we throw a global parade and declare that aliens exist, we have to respect the incredibly strict burden of proof embedded in the scientific method. Right now, the detection of DMS is sitting at a 3 sigma level. That means scientists are 99.7% sure the data is perfectly accurate. In school, that's an A+. But in the realm of astrophysics, when dealing with a claim this monumental, a 0.3% chance of error or signal fluctuation is simply way too high. So to officially confirm a massive discovery like alien life, the scientific community requires the absolute gold standard, a 5 sigma standard of proof. That means we must be 99.99994% certain. We cannot leave room for a single shadow of a doubt.
Which leads us to Part 6, the final verdict. To bridge that agonizing gap between 3 sigma and 5 sigma, Nikku's team isn't just sitting around. There's intense parallel work happening in labs and computer models globally right at this very second. Beyond just securing more telescope time to hit that 5 sigma mark, they're desperately hunting for ethane. In their models, where you find DMS, you should find its byproduct, ethane, and right now, it's a major missing puzzle piece. They also need to ensure they are definitively differentiating DMS from a very similar molecule, DMDS, while maintaining that absolute consistency in the lack of ammonia.
And, maybe most importantly, they have to completely rule out non-biological sources. Scientists in labs have shown that if you blast UV light into a mix of hydrogen sulfide and CO2, you can actually create DMS without any life involved at all. Even though this process currently only yields very small amounts compared to what we're seeing on K2-18b, we have to make absolutely certain that some weird, unknown alien chemistry isn't just tricking us.
As we patiently wait for the next batch of data from the James Webb Space Telescope, keep this in mind. This rigorous, frustrating, and incredibly awe-inspiring process is exactly what makes science so beautiful. We're doing the hard work to ensure that when we finally make the announcement, it is undeniable. In this endless darkness, we are searching for a heartbeat in the noise of radiation. It might not be a heartbeat of blood and muscle, but a chemical one. Will this cosmic heartbeat finally rewrite human history? Keep your eyes on the stars, and we'll see you in the next explainer.